Cosmology. When did the elements form? Hi, I'm Raz Pasha, the narrator of this video. And before we get into it, I have a challenge for you, the viewer. Can a single web page provide the answer to life, the universe, and everything? My guess is probably not. But what about one of life's big questions? Have you ever been surfing the web and come across a website or a web page that holds one of the secrets of the universe? Well, that happened to me the other day. It was simple yet elegant. Not as elegant perhaps as E=mc², but I'll show it to you. I googled radioactive isotope half-life to find it, and here it is. It came from Astro Berkeley Edu. It was a radioactive isotope table listing the isotopes, their half-life and their relative abundance. The table listed all the radioactive nuclei with a half-life greater than 1,000 years, approximately 70 of them. I've displayed just 12 of these on the screen. 70 won't fit, but what I've endeavoured to do is maintain the pattern. Generally those with a short half-life are missing. Those with a half-life of about 700 million years are rare, and those with a half-life greater than 4 billion years are common. So what does this mean? This simple table gives us the ability to form a rough estimate of when the elements that comprise us and the planets were forged. You don't need to be an astrophysicist to do it. Firstly, let's look at what half-life means by an example. If we start with 1 kilogram of radioactive material, any material, we will have 500 grams of material left after a single half-life. If we allow the 500 grams to continue to decay for a second period of a half-life, then we will have 500 grams divided by 2 left. Alternatively, we could say that we have 250 grams after 2 half-lives. Continuing the process, we get 125 grams after 3 half-lives, etc., till we get to less than 1 gram after 10 half-lives. An element decays away below detectable levels in about 10 to 15 half-lives. I've now put the isotope table back up on the screen, so we can calculate a minimum estimate for the age of the elements. Now, a minimum estimate for the age of the elements may be attained by considering the isotope with the largest half-life that is missing from the crust of our planet, that being uranium-236. By multiplying its half-life by the minimum number of half-lives that can deplete an element will give us that estimate. That is 234,200,000 times 10, or 2.3 billion years, and the upper limit is obtained by multiplying the half-life of uranium-238 by 15, and that gives us 66 billion years. So the actual time when the elements were forged or formed lies between 2.3 billion and 66 billion years. This gives us a very broad-based set of limits. We can say with confidence that the elements formed billions of years ago and not thousands, or not millions, and not trillions of years ago. And probably the most likely estimate would be obtained by multiplying the half-life of uranium-235 by 12, and that is approximately 8.5 billion years old. This value fits well with the current age of the universe being estimated to be about 13.5 billion years, and the estimate for the age of the Sun being 4.5 billion years. What about carbon-14? It has a short half-life, yet it is present on the Earth. So why is that so, if elements formed 8.5 billion years ago? The answer is that carbon-14 is being constantly produced in the upper layers of the troposphere and the stratosphere by thermal neutrons absorbed by nitrogen atoms. When cosmic rays, elementary particles shot out by the Sun or distant stars, enter the atmosphere, they undergo various transformations, including the production of neutrons. The resulting neutrons participate in the reaction shown. The small n in the equation represents a neutron. It has an atomic mass of 1. The large N stands for nitrogen, and its nucleus has 7 protons and 7 neutrons, giving it an atomic mass of 14. When a neutron slams into a nitrogen nucleus, knocking out a proton, the new element formed is carbon-14, comprising 6 protons and 8 neutrons. The proton that was knocked out takes with it an electron, making it a hydrogen atom shown as H in the equation. There are isotopes that are rare even though they have a long half-life. Of 35 radioactive isotopes with a half-life greater than 4 billion years, 11 are rare. That's 31%. This may seem as though it needs an explanation. However, when we compare this with the stable isotopes, the situation is to be expected. Of 280 total stable isotopes, about 30% are rare. Now we need to consider what was exactly that we dated. Initially, from the Big Bang, there were no elements, and certainly at the time the first stars were formed, there were no elements larger than hydrogen. Fusion reactions in the stars build the larger elements. When 2 hydrogen atoms fuse together, it makes helium, and energy is given off. A helium atom fused with a hydrogen atom makes lithium, and so the process goes on till we get to iron, which has an atomic mass of 56. Hence, as Carl Sagan said, we are made of star stuff. Anything larger than iron requires a supernova to produce it. Almost every element on the isotope table had an atomic mass greater than 56. What we actually dated was the supernova from which these elements were formed. We know that the solar system must have had an additional source of material, since hydrogen and helium predominate in our solar system today. Before a star becomes a supernova, it consumes all the hydrogen and helium. This means that most of the matter must have come from a gas cloud and not the supernova. Given the evidence, it would suck to be a young Earth creationist. Our estimate was that the supernova occurred about 8.5 billion years ago. Don't forget the viewer challenge. Do you know a web page that provides the answer to any of life's big questions?